Well, thank you so much for the invitation to talk here, and a very good afternoon to everyone. As you heard in the introduction, my background includes both cloud. I was at AWS for many years, and some of the crypto world from my experience down at Coinbase. So a quick caveat here, we're talking about the non-crypto side of blockchain's piece. But it was an interesting opportunity working at Coinbase to get a front row seat to some of the existing technologies. And we'll talk a little bit as we go on here about why some of them weren't sufficient. One of the things that's really, and I don't have to tell people in the room here, about how much semiconductors have become a piece of our everyday lives. And those of us who were at the dinner last night heard Chris talk kind of very eloquently about some of the ways in which semiconductors have begun to permeate everything that we do. Unfortunately, that also means that when something goes wrong, if there's, when there's counterfeiting, tampering, when supply chains even, aren't delivering in the way that we expect, then there are also commensurate challenges. And those challenges have become much more pervasive and serious than perhaps even in the past. So one of the things that's especially interesting about this, and of course PDF Solutions probably knows this better than anyone, is that these challenges are no longer just the province of a single company, a single IT organization, a single system, a single representation. They are inherently cross-company, cross-system, cross-cloud challenges. Amazon, that last quote there is actually from Amazon, who has said that 80% of company data now lives outside of the organization. And that means that challenges around data integration, data security, data collaboration are no longer primarily the province of the IT organization. They've actually become the challenge now across companies and across organizations. Now, you might be forgiven for asking, what does blockchain have to do with this? And what does blockchain actually mean in this context here? And I want to talk a little bit about it from the perspective of relationships. So there's potentially a lot of interesting kind of math and and software algorithmic technology that sits behind some of this. But at the core of it, we're used to these same kinds of relationships and trust building in both our personal and professional lives. Mean what you say what you mean. Show up when you say you're going to show up, do what you say you're going to do. If you get a receipt for something or you agree to something, you remember that and you respect that thereafter. And those same challenges exist in our business relationships. We know these generally as legal contracts, right? They're mitigated by contracts written, often very explicit, by audit traces that ensure the compliance with it. Blockchain at its heart is about the digitization and automation of these same types of trust. That word trust now kind of conveyed into the machine-to-machine language and communication space, so that if you have an IT system and you're hooking it up to a business partner's IT system, those two systems can communicate and collaborate around data, and that data has all those same relationships and trust now built into it. In particular, it's immutable, it's tamper-proof. It can't be changed after the fact. The people who created it, the systems that created it, can't change their minds about it. Everybody sees the same information. And that information, especially, has the lineage and traceability built in and carried along with it. And that's so important for what we're talking about here today, because it turns out in a lot of these cases, sharing the data isn't the hard part. There are times when that actually is a piece of the challenge, and we'll chat about that a little bit. But most importantly, it's understanding who did what, when did they do it, where did it come from? And I was sitting yesterday in one of the presentations here, hearing about, for example, getting test information that might distinguish between whether a chip eventually goes into a tier 1 system, say like an airplane or a self-driving car, or into some tier 2 or tier 3 system. So when many of you who are traveling home or flying in an airplane, you'd like to rest assured that all the devices used in that, for example, went through the appropriate testing regimes, came through with the right level of quality checks and so forth. You'd like, in fact, that bill of materials for the airplane body that you're flying in to be traceable, including their quality assurance, all the way back to their origin and through everyone who handled them and processed them in between, that entire logistics, manufacturing, and supply chain. And then you'd like that to be true throughout the entire life cycle of that airplane, right? Because it's gone through goodness knows how many mechanical and electrical and other updates. And that type of ongoing bill of materials is a great example of the type of this trust replicated into now the world of safety, right? All of us want to fly home and make sure that we actually get there. And so when we talk about improving traceability across the semiconductor supply chain, this is part of what we're gunning for here. That bill of materials that represents a digital and now tamper-proof and secure mechanism so that we can take these end systems that result, regardless of how complex they might be, and work them all the way back to the individual semiconductor components with all those pieces in between. And there's a lot of complex technology here at play, making those standards bodies that Dave was talking about actually replicate into the blockchain requires complex hierarchies of Merkle trees and digests and other pieces in order to make all of that true. But the end result is actually a simple one. It's that ability to mitigate threats around security, threats around counterfeiting, and certainly, and perhaps most importantly, even just the qualitative threat that defects can represent. And on being able to trace that lineage allows us to do this shift left that everybody is gunning for. Detect things faster, detect things throughout their life cycle, and be able to action as we all encounter those different systems at different stages of the manufacturing, supply, and delivery chain, and be able to understand if something does go wrong, how do we trace that back to the point of origin? So that not only is that device as safe and secure and sound as it can be, but over time, entire fleets of vehicles, airplanes, and other devices become safer and better for travel. Now, to do that, you need a few things. Probably the single most important piece is the one that we talk about a lot here at Vendia, which is a single source of truth, by which we mean a corpus of data that's been synchronized and harmonized and where everybody has a shared view of reality. That sounds kind of simple, but in point of fact, this is often one of the foundational parts that's very challenging. Start thinking about, multiple copies of data, just the explosion of data, the number of places that data has to transit to throughout the life cycle of a manufacturing and distribution process. And then being able at the very end of that, let's say, I'm gonna, drive home in my car tonight. If something goes wrong, how do I reach all the way back to the original point of manufacture and figure out where and how was some defect introduced? So getting to that single source of truth is first and foremost a data integration, data sharing, and data collaboration problem, on top of which we need to add things like tamper-proofing. What's funny, of course, is that when I talk to people about this, often the first question I get asked is, can you help me share data? And then the second question I always get asked is, can you help me not share data? Because it's probably just as important, if not more so, to protect the intellectual property, the regulatory requirements. Vendia holds a lot of PII and PHI, and being able to control that data and its ownership across its life cycle is one of the most important things that has to happen here for this to be useful in practice. And as you mentioned before, that traceability and lineage is really important. The actual data sometimes is almost beside the point and doesn't even need necessarily to be on chain. What has to go into the blockchain, rather, are the digests, the tamper-proofing materials, the metadata related to access controls and governance, because those are the things that have to be seen by everyone, shared everywhere, and then ultimately enacted and protected by the system and the platforms underneath. And that, in fact, is one of the most important roles of a platform here, is to protect and provide for that kind of access control and that intellectual property restriction and enforcement at the platform level, so that you can be absolutely certain that not only are people seeing the right data with the right version, with the right source of truth, but also that the wrong people aren't seeing that data, or data that's supposed to be redacted or obscured or obfuscated or somehow controlled has been done so correctly. And then finally, the making sure that that spans the entirety of the workflow from start to finish. I think one of the kind of recurring themes that I've heard here are some of the challenges of carrying data from this very point of origin all the way through to the final sort of receiver, and then being able to tie that back again. And those are, in fact, some of the most challenging problems that blockchains can help solve, because they do tie together this multi-party data sharing and lineage so effectively. And by the way, that's not just in the semiconductor industry. We could have practically that same conversation in the world of travel, in other sectors like healthcare, like financial services, and we'd be talking about virtually the same kinds of challenges. Now, if you listen to the news, you might very well be sitting there going, blockchains, really? Because there's been a lot of negative news here, along with all the positive. In fact, I often jokingly say that blockchains have probably had the most extreme hype cycle of any technology that I've encountered in my career. from going from they can solve virtually anything to the point of being almost ridiculous, to seeing a lot of those early pilots and proof of concepts and initial deployments fail. And in fact, having companies kind of pull back and sometimes pull out based on that lack of adoption or that lack of initial technology credibility. And there's a really good reason for all of this. First generation blockchains have failed for not because the underlying concept wasn't interesting or applicable or that the business solutions weren't well intended, but because they weren't really great technologies. And there are a bunch of ways in which these initial implementations have kind of failed to deliver on enterprise readiness. Scalability, for example. We'll take Ethereum as a good example that most people have heard of in a public chain. Ethereum's capacity on a good day is about 15 transactions a second. Now think about that. 15 transactions, something you can count on your fingers and toes, shared in the entire planet Earth. There are a lot of companies on the planet. I'm kind of guessing 15 transactions aren't going to be enough for all of them. And that type of problem, for example, has limited the ability of enterprises to treat this in the way that they treat data. If you think about a database, maybe a database is capable of doing hundreds of thousands, millions of transactions a second. How are you going to stuff them all into a 15 TPS system that you have to share with everybody else? So that's a particularly good example of places in which these first generation technologies were really challenging to use. No support for data modeling. Think about all the complicated things we've been talking about here over the course of the last couple of days. And now imagine if your job as a software developer is to go figure out how to encode those complicated details and data structures into a string, and then pull it all back out again and not make any mistakes doing that. That's job number one using, say, Hyperledger Fabric, because it doesn't support rich data types and modeling. So without the ability to store data in a database, which is typically all about modeling the data and then ultimately evolving that data model over time, you've got a challenge. Similarly, native file support, SQL support, CSV files, all these things we kind of use in our daily lives. The other one that I'll pick out from here is cloud native. We just heard a talk from AWS. One of the things that, of course, we're increasingly placing our data in the cloud, or we need our data to at least be cloud adjacent. Another thing that's interesting about the public cloud is that it's the densest place you can find silicon today. Look at AWS's US East 1 region. You can measure the weight of the semiconductors. I don't mean the racks, I don't mean the concrete pads or the HVAC. I mean just the chips alone in tons. It's insane how much silicon resides there. And not being able to access that effectively is one of the challenges of these early blockchain technologies, because they weren't designed to effectively leverage silicon. And we'll talk a little bit about compliance here in a minute. So one of the things we set out to do at Vendia, since I kind of came from a cloud background here, was address some of these challenges of first generation blockchain and distributed ledger technologies head on. And we wanted to do this in service of the data integration and data sharing challenges that are similar to what PDF Solutions is doing in the semiconductor industry, and then of course similar kinds of problems in other sectors and industries as well. And when we focus on a couple of things here, like the golden record, producing a single source of truth, because that's common to almost every sector, use case, industry, company that we come across. And then similarly, governance and auditability, because it's often not enough just to be able to share data or provide some kind of tamper-proofing. You have to know who changed what and when. We sometimes humorously refer to this as the whodunit feature, right? Being able to understand not just what the data is, but how did the data get to be that way? Who made what change to when? And are you sure that that was in fact the right change? It's essentially the answer to kind of continuous real-time auditing, defect tracking, traceability, and so forth. And one of the things that's super, super important about this is being able to solve those challenges.